Look, we always calculate any change by using, by let's say combusting a fuel or something, by using a bomb calorimeter and get the change in temperature and the heat transferred. But this is just a change. This is just a change. The standard enthalpy change of combustion. But there's no way we can calculate absolute value. So what we have is we have a reference, and that reference is the standard state enthalpy change of formation. The standard enthalpy change of formation is defined the enthalpy change that results when one mole is formed from its elements. By convention, the standard enthalpy change of formation of any element is its stable form is zero. And like in on the Earth, the potential energy is zero, taken zero here. So similarly, the standard enthalpy change of formation zero. So now, because this is, we can't calculate the absolute, we have a reference. And because that is why we use, whenever we find a reaction equation like the heat of reaction, we just subtract the formation from of products minus reactants, and we are actually taking from that reference, and we get the, so we a reaction can be found, that change can be found from that reference of formation. The other thing you have to understand is that these are like, if you formation of equation of nitric acid is this, but this is only a theoretical equation. This might not occur in nature. So sometimes we use theoretical equations to get the the equation, the formation value, because it will all end up in the right way by, because everywhere we are doing this. And the other thing is the standard states you should know, like ammonia is a gas at this at this temperature and pressure. These are the standard 1 kp and 298. That means that's nearly room temperature. You find this to be existing as a gas, this as a gas, ethane as a gas, ethanol as a gas, and ethene gas, water as a liquid, pentane as a liquid. So these states are very important. So whenever we uh, all the states should those occur under standard. So he's saying hydrogen, nitrogen, and all these are gases to get nitric at liquid. So this exists as a liquid and the others exist as gas. So this is the equation. It's a theoretical equation, and this is used to find the formation, and then it is used to find the change in, because this is the reference change in the reaction, the enthalpy change reaction. The other thing is the although standard articulated rate may be necessary to determine the standard of a compound before it can be used elsewhere, they may be used. This can be used data formation from its elements such as enthalpy. You can get the formation from combustion also, and so here, for example, carbon dioxide form burns in according to this graphite plus this plus this. This equation is the standard state of formation of carbon dioxide and is also the equation of graphite. So this is burning graphite and also the formation of. So we can use this equation and the standard enthalpy change of combustion of graphite to find the standard enthalpy change of formation of CO2. So we need the enthalpy change of formation. We know that this is combustion also. We What we can do is, so we are trying to find this enthalpy change of formation of CO2. You can say, how do we find this? Well, we know this is combustion. Now what we do is we say, okay, combustion is equal to 1 mole of formation. This way 1 mole of formation and 1 mole of this. So now 1 mole of this is zero. This is also zero. This we want to calculate, we take it to the other. This is minus 394. So all this goes to the other side and minus 3. So this is the formation we got, minus 394. Important to remember the basic structure of fuel such as reacts with oxygen. So this is how you find the equations of formation. And remember these states. The other thing we have to please understand is whenever these are the coefficients are important here, uh, should we always be taken actual, unlike other equations which they can use an molar ratio. Here we actually, what happens, we use the actual in equation in thermochemical equations. uh, if it's reversed, the sign of enthalpy, when the coefficients are multiplied by some other words as they're happening, then actually, then the value of the enthalpy will change. So actually is what is measured, like in the Baum calorimeter. And if you divide it by the ratio by half or something to find, they'll apply Hess's law or some do like something, will halved. Reverse, it is change sign. And states are very important. So please, because the states will, if it's sometimes like here is using liquid, here it is using gas, so there's a difference in the combustion equation. For example, in the combustion of methane, uh, change the value of, okay, when the same equation written with water vapor, naturally because he's now converting uh, here liquid, here gas. So it's different, no? So enthalpy, the difference is caused by the endothermic reaction when 2 moles of liquid is, so it reduces by 88. And the other thing is the increases by 88, sorry. And the other thing is we can construct a stamp and calculate. Okay, we can do all this by using Hess's law.